Alright class, this is the video on continuity. Continuity just takes limits to the next level pretty much. With limits, as long as it was approaching the same value in the y from both sides. So for example, at x equals 2 here, we can say that the limit would be 1 because from the right and from the left it's equaling 1. However, continuity, you have to look and see, does the graph break anywhere? Okay. So it can have a limit, but it might not be continuous. And for example, on this graph here from 0 to 4, we would say that it's continuous. And I can't spell already. Continuous everywhere except when x is equal to 1 and when x is equal to 2. Because at 1, if you're drawing along the graph, all of a sudden there's a break and it jumps back up here. And then when you hit x is 2, there's a hole. And we're going to talk about what those are called. So basically, in order for a function to be continuous, it's continuous at an interior point if you have a limit and if the value of the function equals that limit. So imagine having this limit here again, and then having this hole filled in. Then it would be continuous because the hole would be filled in and it would have a limit. It's continuous at a left or right endpoint if the value equals, so a left endpoint, for example, would be over here. Like if that's the endpoint, we would say it's continuous approaching from the right if approaching from the right equals that final value. And then the same thing for a right endpoint. If the limit approaching from the left equals the value, then you have continuity. Alright, so you guys know how to find these actually with rational functions. Find all points of discontinuity of this function, and generally they're where the graph doesn't exist or can't happen. So for this one, you should already be able to tell me the function does not exist at x equals 3. So that's a point of discontinuity. So it's discontinuous at x equals 3. Now we did this before. If I wanted to know what the y value would be at the place, we would have to factor this, and let's do that. X minus 3, x plus 4, all over x minus 3. And sure enough, these cancel, and we're left with the function x plus 4. Which means that that was a hole that we canceled out. And we're going to talk about the different types in a second. So we have that the point of discontinuity is when x is equal to 3, and if I wanted the actual coordinate, I would say it's at 3, 7. That would be the point that doesn't really exist. But really I care about more of where the x is. Alright, so now let's talk about types of them. Well, we just talked about a hole. It's also called, actually in the textbook, removable. So if I have a graph, you might see a function like this, and you might even see a dot here. I mean, that could just tell you that the function is, it doesn't have to have that. Both of these are basically removable if the dot was there or if the dot wasn't there. As long as there's a hole in the graph, that's removable. Jump means that we have a split. So all of a sudden it jumps from one value to another in the y at a certain x point. And that's usually shown with a gap. And you'll see those a lot with piecewise functions. And then infinite is when you have an asymptote. So for example, a vertical asymptote, you might have the graph go like this. And this graph goes everywhere except for it doesn't connect right here. There's a wall, so it's an infinite discontinuity. And then oscillating just means that as you get closer to 0, sometimes it oscillates faster and it doesn't approach a value from the left or the right, the same one. You will not see those as often, so I wouldn't worry too much about that one as I worried more about the other ones. So now this one says give the extended function of the same thing we just looked at up above. Okay, well we already know that there's a hole at x equals 3. Okay, so if there's a hole at x equals 3, then we're going to put in well, once we simplify it like we did before, we get x plus 4. So this is basically the graph of this without the hole. So this would be the actual function that would cover the whole thing, or one way to also write it is as a piecewise where we complete the whole. So to complete, we have 3 plus 4, which is 7. So we can write this as a piecewise function. This function can be given as this big function here, when x is not equal to 3. So this exists everywhere except for at 3, and then we would say that the function itself is 7 when x is equal to 3. And by doing that, I have now basically filled in the hole. Basically what this looks like is at 3 we had a hole up at 7, so my piecewise function looked like this, and then all of a sudden I'm now saying, but at 3 I want 7, and by doing that we fill in the hole and made it continuous. Okay, so that's the extended function. Okay, find points of discontinuity and continuity, and then identify the type of discontinuity for the function. Well, this one here, again, we have a bottom where we can't have it be equal to 0, so x cannot be negative 2, just by looking at that. Now, nothing cancels out, so we know that it is, well, first we're going to say it's discontinuous at x equals negative 2. And hopefully you guys realize that since nothing cancels out, it is an infinite discontinuity because we have a vertical asymptote there. So we have an infinite discontinuity because it's a vertical asymptote. And then we would say it's continuous for all reals except when x is equal to negative 2. And you can look at that graph if you needed to see it, but hopefully you guys are good with just knowing that that's a vertical asymptote, so there it's discontinuous. Alright, so last one, give formula for an extended function that is continuous at x equals 1. So this is going to be just giving the formula because this will extend it at that spot. Let's see, first we have to factor this because we don't know what's really happening. So by factoring the bottom, you see that there are 2 points of discontinuity, and then we have to use our difference of cubes up here to factor that. So what happens is we have a hole here. So at x equals 1 there was the hole, and the function that will continue it is what's left over. So we would say the formula for the extended function at x equals 1 is f of x is equal to x squared plus x plus 1 over x plus 1. Because if we put 1 in, we'll get a value, it will fill in the hole there. However, I didn't ask for this, but if I did, if I said where else is it discontinuous and is there an extended function, we would say it's also discontinuous at x equals negative 1. It's infinite, and therefore we cannot come up with, there's no extended function at infinite discontinuities. There are extended functions for holes because you could fill those in by just removing the hole part, but there's no way to fill in an infinite discontinuity because it's a different type of thing. So that is continuity. Alright, that's all.